how's it going? This is Mike coming back at you with another video on discrete mathematics. In the previous video, we saw some examples with predicates, seeing how we assign values to the variable or variables in the predicate to determine whether or not they are true or false for those particular values. And then we saw examples of quantified statements. We saw each of our three quantifiers being used in various cases, and we saw when these quantified statements are either true or false. We're going to wrap up this portion of our introduction to predicates and quantifiers by taking these guys a little bit further and bringing in conditional and biconditional statements, including quantifiers as well. So we can take conditional statements, something of the form P implies Q, and in this case, P and Q are going to be predicates on their own. So we'd have P of X and Q of X, say, and we can throw in quantifiers with them. And when you take a conditional or a biconditional statement, which has two different predicates, P of X and Q of X involved, and you put a quantifier in front of it, you get what are arguably the most commonly seen types of statements in math. Now, it's not so commonly seen up until this point, but if you go on to take higher level math classes like abstract algebra, real analysis, complex variables, and even courses higher, you'll see that when you look at the statements of theorems and when you even look at the proofs of these things too, you will start to see these types of statements showing up. You'll see a conditional statement as well as a quantifier. The two most commonly seen types of statements that we see are universal conditional statements and existential conditional statements as well. But out of those two, the one that's by far more common that we see is the universal conditional statement. And for the most part, we're going to focus on this guy here. So if we have a domain, and this time I called the set that is my domain, I called it capital U. Again, what name you give to it really does not matter. But you have your domain capital U and two separate predicates P of X and Q of X. Then the universal conditional statement is of the form for all X in U, if P of X, then Q of X. Now there is another way we can restate this. We can restate this by just assuming that we're only going to work with the X values, the guys in U, that will make P of X true. Now there could be now, this could be a subset of U, it could be the whole thing, but whatever set of things that make P of X true, we're going to give this new set a new name, and we're going to call it capital D. So taking this guy right here, we can restate this as saying for all X in D, Q of X. And we are just saying that, okay, D is just all the guys that were in U that make P of X true. And if you think about it, U and D should be the same thing because of the universal conditional statement. This right here guarantees that it is true. This guy right here may or may not be true. So there is a little bit of difference there as far as what those things are saying. There is another type of statement that we do see quite a bit, This guy, probably about as common as the universal conditional statement, definitely more common than the existential conditional statement. We have the universal biconditional statement, which is of the form for all x in some domain D, P of x if and only if Q of x. So very similar to the universal conditional, but that was if P then Q. This is P if and only if Q. Now, I didn't necessarily provide an example of an existential conditional statement here in my pre-written notes, but you can probably guess approximately what this kind of thing would look like, just given our knowledge of what conditional statements look like, as well as how the existential quantifier gets used. You could say it something like, there exists x in D, and the s dot t dot is just short for such that if P of x, then Q of x. So that's just what an existential conditional statement would potentially look like, but we really don't encounter these that much in the world of mathematics, so we don't really mess with those that much. So we've taken these really common types of sentences and really common types of statements, and we've put some symbols to these things to make writing it shorter. Well, for some reason, this wasn't short enough for mathematicians, and they had to further symbolize this and further shorten it. Instead of saying this, we can also use implicit quantification symbols that both take care of the conditional or the biconditional statement that we want to have, but it also takes care of the universal quantifier. These are pretty much only used, and all we're going to look at in the cases where we'd have a universal quantifier. So if we have two separate predicates, P of x and Q of x, that have a common domain D, P of x implies Q of x, and note that this is a thick rightward pointing arrow, means that every x that makes P of x true also makes Q of x true. This is the further symbolization of saying for all x in D, P of x implies Q of x. So strictly what this thick arrow means is that the sort of implied background knowledge, if you will, is that we are doing this conditional with all the x values that are known to have made P true. So there's no extra thing that we have to check. There's nothing else that we have to do here. Similarly, P, and then this is obviously a thicker left and right pointing arrow. Q of x means that P of x and Q of x have exactly the same set of values x that make them true. This is the further symbolization of for all x in D, P of x if and only if Q of x. And here we have the less thick left and right pointing arrow. Now, when it comes to the thinner arrow versus the thicker one, for the most part, you'll see me use these. If you go on to take higher level courses with me, I'll use these pretty much interchangeably. I think most people probably would use this pretty much interchangeably, whether we use the thin arrow or the thick arrow when we're writing a conditional or a biconditional. We're just pretty much assuming that we are working with all the x values that make our hypotheses p of x true. So there's not really too much you have to worry here with the thick arrow versus the thin one. Just note that this is out there and know that you may potentially encounter this slight difference in notation. But the big thing really here for this video is with the universal conditional statements as well as the universal biconditional statement. These are the two most common types of statements that you see in the world of math. Most theorems that you have encountered in previous courses, as well as ones that you will continue to encounter in future courses, all of those theorems take on a form like this. So this is it for the end of this video. In the next video, we are going to see what do we do when we have these types of quantified statements and when we take the negation of them. What does taking the not of a quantified statement do to it? How does it change it? So if you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.